Okay, so we've got a couple questions for office hours today. There's just a few people here, and it looks like we're mostly going to be going over conceptual questions. All of these are from the crystal structures. And we're going to be looking at number 8, which is a conceptual question about body-centered cubic. And then we've got 15, 20, 22, and that's the problem that combines together all of the thinking of how does our idea of periodic trend and lattice energy combine together to kind of explain the structures we're seeing. In order to look at this, we're going to look at some things on the computer. So let me go ahead and share my screen. We're going to start with number 8. And to understand number 8, we're going to look at this crystal structure simulator, and we're going to look specifically at body-centered cubic. And the thing that's kind of funny about this is the coloration we're looking at here. So number 8, the question for 8C is, why do the gray atoms and the red atoms have the same coordination number in BCC? And that is a kind of straightforward question, but it's not necessarily obvious. So it turns out that if we look at the legend, you notice there's no red or gray in the legend. There's nothing that tells us, oh, red atoms are this, gray atoms are that. That's because actually, for the simple cubic, where we've got all gray, for the body-centered cubic, where we've got this flip, or the face-centered cubic, where we've got the red, gray, and blue, those changes in coloration are actually just to accentuate the layers. So if we look at body-centered cubic, all of these actually could be gray, and we'd be looking at the same thing. The coloration here is just to accentuate the layers. So it makes sense that the red atoms and the gray atoms end up with the same coordination because they're actually the same things. In fact, let's see if we can do this kind of funny orientation of it. And I've got to get my pausing just right. So if we looked at this gray layer and we got rid of it, the red layer is essentially identical to the gray layer. It's just shifted a little bit. Looking back at this gray layer, if we just moved the gray layer diagonally a little bit, it would be exactly the same. So even though that these are two layers, the layers themselves are offset from each other, each layer is actually identical, and we'd end up with the same coordination number. It's also the reds and the grays are artificial difference. This would all be, if we were looking at an actual chemical compound, all of these would be the same thing. We see pure compounds like this. Metals will sometimes have a crystal structure that's body-centered cubic or face-centered cubic, something like that. So we will see things where it's like gold atoms take on a body. I have to double check, but let me check real quick. So some forms of iron are body-centered cubic. Let's see. I was trying to find a list of elements that actually take on the different shapes. Because these are actually representing physical things. Oh, here we go. I found it. There's a fantastic table on, let's see if I can find it on here real quick. Periodic table crystal structure. So so you don't need to know this, but I think it's interesting. I think it's fascinating. If we look at the periodic table, we can see vanadium, chromium, manganese, iron. Those take on body-centered cubic structures. If we look at like nickel, copper, silver, palladium, platinum, gold, those take on face-centered cubic. And you'll notice there are some other weird ones that we could also get. Orthorhombic, rhombic, hexagonal. There's some other structures that we didn't really talk about. And you'll notice the simple cubic comes up very rarely. Most are face-centered cubic or body-centered cubic. But we can actually look at this and say, if we were looking at iron in a body-centered cubic system, that would be all of these, the reds and the grays, would all be iron. It's just a trick. So hopefully that explains that aspect. Going on to problem 15, 20, and 22. This is asking us to look at, let me make sure I've got the question correct. This is asking us, how does the coordination number and ion number relate to the predictions we made from periodic trends? Is there good agreement or not? So when we look at our periodic trends, when we're looking at, if we got to that point, hopefully we've got things like we've got CaF2, we've got NaCl. For our empirical formulas, empirical, not empirical. Empirical formulas, we've got our coordination numbers. Calcium has a coordination number of 8. Fluorine had a coordination number of 4. And we've got our atom count, where calcium had a count of 4, fluorine had a count of 8. It kind of flipped. Sodium had a coordination number of 4, chlorine had a coordination number of 6. Oh, I was thinking of atom count instead of coordination number. Wait, is it 6 or 4? I have to look at the simulator, but let's just, I know that the atom count is 4 and chlorine is 4. To get these, you should look at the simulator. Don't just watch the video and get the answers. But the question is, how can we relate all of this information to the periodic trends, and is there some self-consistency there? And now I want to double check. If we look at sodium chloride, it is 6 and 6 for the coordination number. You'll notice NaCl has a 1-to-1 ratio, NaCl has a 1-to-1 ratio, NaCl has a 1-to-1 ratio. Same thing, calcium fluoride, we've got our 1-to-2 and 2-to-1. And you might look at that and be like, well, how is that self-consistent? Let's go back to thinking about the periodic trends. So I'm going to share a different screen with you now. Let's see. Ooh, I don't know. This will be interesting. So I don't know if the recording I'm making will catch the drawing I'm doing in Zoom. So if this isn't showing up on the video, I'm sorry. But for those of you that are in office hours, hopefully this will make sense. We've got a couple things that we can say. From our periodic trends, if you're like, I don't remember the periodic trends, go watch the video. But generally, we've got this trend for radius, where as we go from the noble gases, neon, argon, all the way over to our alkali metals, lithium, sodium, potassium, our radius gets larger. And as we go down the periodic table from lithium to cesium, our radius gets larger. And then we also have our ionization energy, which is how difficult it is to remove an electron. And it turns out these things that have big radius, it's easy to remove an electron from. So we end up with kind of, for ionization energy, we kind of end up with our arrows pointing the opposite direction. We have a larger ionization energy over at neon, argon, fluorine, chlorine. Harder to remove electrons from those with the small radius. Over on the rubidium, strontium, barium, cesium side, those big radius, easier to remove electrons from those. And then we also have electron affinity, which is how well does something pull electrons towards it? And that also does the opposite of radius. Those things in the top right-hand corner, neon, fluorine, chlorine, argon, those attract electrons towards, well, actually, sorry, we got to change that a little bit because the noble gases don't attract electrons to them. So we should stop at fluorine, chlorine. Right? So when we're looking at this, for the attraction of electrons, electron affinity, affinity is how much you like something. So electron affinity is how much do they like electrons. Fluorine, chlorine, oxygen, sulfur all have high electron affinity. They pull electrons towards them. Over here, lithium, sodium, potassium, rubidium, cesium, calcium, all of those alkali metals, alkaline earth metals, they're not likely to pull electrons towards them. For that reason, we end up with this really predictable things in the first column, pardon my drawing, are likely to form a +1 charge. Things in the second column, that's a 2, are likely to form a 2 charge. Our noble gases are likely to be 0. Our fluorines are likely to be -1, and our oxygens are likely to be -2. And we can justify this through several different ways. We can look at it in terms of the competition between the ionization energy, the electron affinity, and the radius, and how those periodic trends relate to each other. We can also look at it in terms of the quantum mechanics we learned last week, in the idea of where do we get a full shell? Do we need electrons to get to a full shell, or do we lose electrons to get to a full shell? And really, it's the interplay of all of those things, the 3 periodic trends that we're learning and the quantum mechanics from last week that give the combination of this idea of likely charges. The reason I only did those 5 rows, the +1, the +2, the -2, the -1, and the 0, is everything else is a bit harder to predict and has special exceptions. And we'll look at those a little bit in next week and the week after, as we start looking particularly at carbon and nitrogen next week. But we have these relatively predictable trends. So let's go back to the whiteboard and see if we can make sense of what this should look like.
Question, so kind of about the same thing.
Sure.
Now that we have those 5 rows that we kind of memorize and have down, what do you recommend of how do we study or learn further to, like, once we get to these junctions of, like, exceptions, how do you best, I guess, what's your advice of, like, the best way to learn?
Okay, so we've got in our periodic table, I'm going to give like a quick rough sketch of the periodic table because I don't know if the stuff in video really showed up properly. We've got our noble gases there. We've got -1, -2 for those back. And then we've got 0 for the noble gases. We've got +1, we've got +2. Those are the predictable. Everything else is variable. And it turns out that the nice thing about chemistry is we're not really going to be looking at these things in a vacuum by themselves, right? They're always going to be next to something else that's more predictable. So we'll be able to kind of figure out, like, if iron is next to 3 chlorines, the 3 chlorines and the predictability of the 3 chlorines will let us figure out what the iron is. If the chromium is next to 2 oxygens, the predictability of the oxygen on the periodic table will let us figure out something about the chromium. If we did just have iron metal by itself, 0 charge. Anything by itself that's not attached to something else has a 0 charge.
So as we move into next week, kind of understanding those 5 charges on those 5 rows will kind of help us with the more variable elements.
Well, more than next week, the week after, when we start talking about types of reactions and we get into reduction and oxidate, well, I guess that's week 7 actually. So in like 3 weeks, these charges are going to come back. And then we'll use this kind of we'll have chemical compounds and we'll be able to tell from that. So do these predictable trends make sense with this stuff? Is kind of what the question is getting at. Let's start with sodium chloride. It's a little bit easier. Sodium, if we're looking always, whenever you're doing chemistry, periodic table handy. If we look at sodium, it is element number 11. It's in our first row. First column. Third row. It's in our first column. That's the alkali metals. So it's going to be one of these +1 charges. So I'll go ahead and I'll label sodium with a +1. I'm putting it in parentheses because I know that's a trick that I used to figure it out. This compound by itself is neutral. It doesn't have a charge. And then I'm going to look for chlorine. Chlorine is here in the halogens below fluorine. It's going to have a -1. And just from the sense of charge, from the periodic table and this kind of predictability, we can see that sodium with a +1 and chlorine with a -1 kind of makes sense for this thing to be overall 0. If I did +1, -1, I get 0. That's going to be a neutral ionic compound. And whenever we're looking at ionic compounds, the stable ionic compounds, we're generally going to be looking for those neutral compounds. So that is what we call a charge-balanced sodium chloride. This idea that we've got a 1-to-1 ratio because of the charge is communicated through the coordination number, 6 and 6. You got 6 pluses that attract 6 minuses. Or through the number of atoms. You got 4 pluses, you attract 4 minuses. So that works out in that way. So for problem 20, looks great. What about for 21, the calcium fluoride? This one's a little trickier because in this situation, our charges don't match up with each other. They're different. But again, periodic table. Fluorine is the easy one to do. It's in our halogens. That means fluorine is going to be a -1. I'm switching colors just to be dramatic. And you find calcium on the periodic table. Element number 20. It's our alkaline earth metals. It's going to be in our +2 state. So now when we look at this one, I've got my calcium has a +2, and I think, okay, logically, how many -1s does it take to balance a +2? And it would be 2, right? If I had +2 -1 -1, that would be equal to 0. Or another way to write that is +2 plus 2 times -1, right? So what I'm doing is I'm doing the charge on calcium plus the charge on fluorine times the number of fluorines. The charge is balanced. So we have a charge-balanced compound. My positive charges and my negative charges balance each other out. And when we look at the coordination number, that makes sense with the charge. My calcium has more charge. It's got more things next to it, right? The bigger charge can pull more things towards it. So that makes sense that calcium would have the larger coordination number. And in terms of how much larger, it's exactly twice as large because the charge on calcium is exactly twice as large. Now, the reason that flips for the atom count is because when we look at the number of atoms, how many calciums for the number of fluorines, we get this kind of flip. And what you'll often see is you'll see this kind of like arrow drawn thing, where if you know the charge, you can figure out the subscript, or if you know the subscript, you can figure out the charge. That kind of arrow trick only works for these simple ionic compounds. As we get, so this works great in a high school class. As we go on to polyatomic compounds, polyatomic ions, this arrow trick will not work as well. It'll still kind of work, but we have to have like another layer of thinking on top of it. So back to 15-20-22, I don't think I had a very concise answer, but hopefully that's all of the ideas that we can put together to kind of explain periodic trends give us predictable charges can give us ratio of atoms, and predictable charges give us coordination number. We can start at any one of those spots. We could start with predictable charges from the periodic trends to explain coordination number and atom count, or we could use atom count to explain coordination number and predictable charges, or we could use coordination number to get predictable charges and atom. Like, it's a circle, and any place where you start, you can kind of like follow it around and get an explanation for all of them, hopefully. But that's what I'm showing you here is the way that my mind kind of puts it together and thinks about it. Okay, so we just had another question come up. We're looking at the week 3 practice number 5. I'll go ahead and read that question real quick, and then we'll look at it together. So this says, consider the highest energy orbital in phosphorus. Enter the number of electrons at this energy level. At this point in chemistry, we always get our periodic table handy. I'm going to go ahead and just write the entire electron configuration for phosphorus as I start to think about it. So I'm not going to use the shortcut. I'm just going to read it off the periodic table. I'm going to use 1s2, 2s2, 2p6. Actually, we will use the shortcut. 3s2, 3p3. The shortcut for this, so this is looking at phosphorus. The shortcut for this would be neon, 3s2, 3p. Wait, did I say? Yep, 3p3. Okay. Thought I messed that up for a second. And we say, okay, highest energy electrons. How many highest energy electrons? There's this kind of...
energy electrons valence electrons?
Pardon?
Is highest energy electrons valence electrons?
Typically, yes. Right? So when we look at this just in terms of the number of valence electrons, it's really going to be, if we look at this, we have to think back to week 1 a little bit. Actually, I guess week 2. But you remember how we had these energy plots where we had n equals 1, n equals 2, n equals 3? Right? This was energy plots. It turns out that when we look at this, these electrons are n equals 3, L equals 0. These electrons are n equals 3, L equals 1. But both of them are in the n equals 3 state. So they're all going to be in the same energy level, roughly. Again, I do quantum mechanics. This is kind of my thing, so I'm like, this isn't exactly true if you apply a magnetic field. There's all kinds of weird things we could do to mess it up. But for kind of a first pass, a first kind of thinking about things, we recognize that everything that's in the level 3, that's n equals 3, is going to have approximately the same energy. So that would be 5 electrons in phosphorus would be in that outermost shell.
And so are the core electrons counted all the way up to the next noble gas?
So
this is kind of like a different kind of question.
Okay. So we count the, there's kind of also some debate about this. I think it's okay to say the core electrons are everything that's the previous noble gas, right? So everything back to that closed shell. There is a kind of nuanced additional answer, which is if you filled your d orbital, it becomes not, like when we talk valence electrons, the real thing we want to focus on is reactive electrons, electrons that we can interact with and cause that participate in chemical reactions or electrochemistry or some other thing we can do. Valence electrons are those electrons that we can easily interact with. And typically that's everything outside of the closed configuration, everything from the noble gas up. We get into a little bit of extra weirdness when we start looking at our d orbitals. And if we fill a d orbital, we get all 10 electrons kind of in their pairs together. Those electrons start becoming non-interactive, and so we don't count those as valence. For me, in a Gen Chem class,
can be up to zinc and cadmium and mercury.
Yeah. So, but for a Gen Chem class like this, I'm kind of okay with just saying up to the noble gas configuration is the core, and then everything past the previous noble gas configuration is valence. Again, that's true 90% of the time. There's some exceptions to it, but it's right most of the time. Cool. Okay, so next question up is mastery question 4, number 5. This one is asking us kind of electron configurations and how we relate to the quantum numbers we learned last week. So the question is, if L is equal to, at least the question I have, I don't know if it's randomized for you, if L is equal to 3, what is the letter code? What's the highest possible M sub L? What's the lowest possible M sub L? How many values of M sub L are possible? Letter code is case sensitive. So the letter code part is part of the electron configuration. This is actually a really important detail that some people have missed out on. So we have our L value 0, 1, 2, 3, 4. Ooh. We use a letter code because it kind of gets, there's a historical reason and kind of practical reason. The historical reason has to do with kind of the original spectroscopy that was done for materials and kind of the way that the light responses looked. It's also kind of just written nicely. So you can imagine how it would look if I wrote 1s2 versus 1, 0 squared, right? This becomes harder to kind of parse apart what's happening if we just kept using the quantum numbers. It becomes really difficult to tell what's going on. So we use these letter codes. And then, so for mine, I've got L equals 3. I would use letter code lowercase f. And these are all lowercase. My S looks big, but it's lowercase. Then for the max values, we have to go back. The quantum numbers video tells us that if we're looking at L equals 3, M sub L could be all the way from -3 all the way up to +3. So for this L equals 3 situation, there's all of these different possible orientations of the orbital. So my maximum value would be +3, my minimum value would be -3, and I would have 1, 2, 3, 4, 5, 6, 7 possible M sub L values. Now, did you also have L equals 3, or did it randomize?
I had L equals 2.
Okay.
Now that you explained it, I actually figured it out.
Great. Fantastic.
But yes, I just was confused on letter code. But
yeah. So the thing you asked me about before I started recording was the n equals 4, L equals 3, M sub L equals 0, M sub S equals +1/2. This is a set of 4 quantum numbers. That's just the simplest name for it. This is a set of 4 quantum numbers. This is the letter code for the angular momentum operator, angular momentum quantum number.
Okay, got it. Thank you.
You bet. Okay, so just got the next question, which is looking at mastery question practice problem 6, which says, use this graph of successive ionization energy for questions 6 to 8. So first, let's make sure we have a good understanding of this graph. Essentially, to remove the first electron takes some amount of energy, right? A little bit of energy. Removing the second electron takes more. Third, fourth, fifth, sixth, and after we get to the 6th electron, we see this huge jump in energy for how easy or hard it is to remove an electron. So we have 6 electrons that kind of, every time we remove an electron, of course, it gets a little bit more difficult to remove an electron because you've got the same number of protons attracting fewer and fewer electrons, which means the protons can kind of pull in more and more. But this big jump, that suggests there's some other change besides just the number of protons. Something else has changed. What's most likely the change there is we ran out of valence electrons, and this is trying to remove core electrons, right? We're changing, that's a change in the shell. So let's go ahead and look at problem 6. If the element, so mine says if the element is in the second row of the periodic table, which element is it? So I'm going to go ahead and look at my periodic table. I can look at it here. I'll pull up this crystal structure periodic table. So if I'm in the second row, I'm going to lose 6 electrons easily, so I'm going to count over 6. 1, 2, 3, 4, 5. I'm going to say mine's oxygen. That's 6 electrons lost before I get to an empty valence and start trying to remove core. So I'd remove those 6, and then I'd see a giant jump up in energy when I start trying to remove the core electrons. So I don't know if it changes second row, third row, but for the picture I have, I would say oxygen. What is the label of the orbital from which the electron is removed in the 6th ionization of the element? Enter the orbital label. So in the 6th ionization, 1, 2, 3, 4, 5. My 6th ionization would be removing that last electron of oxygen. So that would be, first electron removed would be there, 4, 5, 6. That would be removing an electron from the 2p orbital in the 6th ionization. Sorry, 2p, 2s orbital. What is the label of the orbital from which the electron is removed in the first ionization? Again, if it is oxygen, that would be a 2p electron being removed. So it's a little bit of investigative work in kind of understanding how valence electrons and core electrons relate to this idea of ionization energy and this jump of it becomes much more difficult to remove electrons after you've removed all of the valence electrons. Did that make sense?
Yeah, I just didn't get the graph.
Ah, okay. Yeah. So it's that kind of interpretation of the energy jumps.